Hello again. In the previous video, we have already discussed on how to improve the steady state performance of a certain system by introducing a PI controller. We also have discussed on how to design PI controller in the previous video. In this video, I want to discuss on how to design another type of controller, which is referred to as a PD controller, a combination of proportional and derivative action in our controller. Before we discuss on how to design a proportional and derivative controller, let us take a look on what is the benefit of PD controller. In the previous video again, we have already discussed that PI controller is a good controller. It's a perfect controller if we want to improve the steady state performance of our system. On the other hand, PD controller is more appropriate if we want to improve the transient performance. For example, if you have a system that originally is oscillating too much, like what you can see here, the black curve here illustrates the step response of a system where the performance in terms of the transient is not really good. As you can see here, the uncompensated system has a more oscillating response. If you want to reduce the oscillation and you want to have a less percent overshoot in your response, it is a good choice to use a PD controller. At the end, your system will be less oscillating. Okay, let's take a look now on how a proportional derivative controller looks like in terms of its dynamic. Pretty similar like what we discussed in the previous video when we were discussing PI controller. Let us now consider the same thing. We have a unity feedback system where GS here is the system that we want to control, the system that where the performance is going to be improved by introducing a controller GC here. But now in this particular case, let's consider GC as a PD controller. As the name implies, PD controller consists of a proportional gain and a derivative action. Kp is the gain of the proportional part and Kd is the gain of the derivative action there. I can also rewrite this equation. I can manipulate the equation mathematically into a form like this, where now I will call Kd as Kc, a gain of my controller Kc, and the ratio between Kp and Kd as a new variable of Zc. So as you can see here, basically a PD controller is a dynamic system which contains 1 0 on it. If we are going to sketch the Bode diagram of this dynamic system, the dynamic system of a PD controller, you will see, using a straight line sketching, the Bode diagram will be like this, where the magnitude plot at low frequency, it will have 0 slope, but at high frequency it will have an inclined magnitude plot with a slope of positive 20 dB per decade, right? Where for the phase plot, we will have 0 degree at low frequency and 90 degrees at high frequency. So looking at this behavior, we can also see that a PD controller the effect of this PD controller is it will add a phase to the system that we are going to control. It will add a phase because at high frequency the phase will be increased, and then we will have a more positive effect on the angle of the system that we want to control. Let's take a look now the following example. Let's consider a very simple system that we want to control. We have a simply double integrator system like what you can see in this slide. So we have a double integrator system 1 over s squared, and we want to control the system in order to improve the transient performance. We are going to control it by introducing a PD controller here. So GC here will take form of a PD controller. As usual, when we are going to design a controller, we have to come up with a design requirement, a design specification. It's different from the typical requirement when we are designing a PI controller, because PI controller is meant for improving the steady state performance. As I have already mentioned before, PD controller is more suitable to improve the transient performance. So in this example, the example of a PD controller design here, the requirement is we want to improve the transient performance. Transient performance can be represented as a requirement of certain damping ratio to be achieved and certain undamped natural frequency to be achieved. Why is it like that? Of course, because if you are referring to step response of a second order system, zeta and omega n, these two variables will dictate the features of a step response in our second order system. Those features are settling time, peak time, rise time, and maximum overshoot. So all of these features that will define the transient performance, everything, all of these 4 features are driven by zeta and omega n according to the formula. Okay, so whenever you want to improve the transient performance in terms of zeta and omega n, or even in terms of settling time, peak time, maximum overshoot, and etc., etc., you have to introduce a PD controller. Accordingly, you have to design an appropriate PD controller. Okay, now let's go a bit deeper on designing a PD controller for this double integrator system. Now, let's get back to the problem here. I have a double integrator system, but I don't like the transient performance. I want to improve the transient performance. I have 2 requirements, as you have already seen in the previous slide. One of the requirements is that I want to have a zeta less than half of square root of 2. This will be more or less equal to 0.707. So the first requirement is that I want to have this system, the double integrator system, to have a zeta less than or equal 0.707. Of course, same like what we did in P as well as in PI controller design, the dynamic requirements have to be translated in a frequency response requirement, and the frequency response requirements can be the requirement of a phase margin frequency, a gain margin, or gain margin frequency. We have already discussed the relationships between zeta and omega n to phase margin frequency, gain margin, and gain margin frequency. So what I'm going to do now, I want to translate the damping ratio, the zeta requirement, to phase margin requirement using this formula. You have seen this formula before, right? So the requirement of zeta less than 0.707, I can translate it now into the requirement of phase margin less than or equal 65.53 degrees. You still remember also this plot that we also discussed in the previous few videos, the relationship between phase margin and the damping ratio. When we want to have, let me switch again to pen, when we want to have damping ratio zeta less than 0.707, I'm not sure, probably it's somewhere here, this will translate the requirement of phase margin less than 65.53 degrees. Okay, so this is the first requirement translated to the requirement in phase in the frequency response function. We want to have phase margin less than or equal 65.53 degrees. When will this happen? If we look at the Bode diagram of the original system, the double integrator, we can easily see here that a proportional controller, if we introduce proportional controller only, if we only introduce proportional controller, this requirement cannot be achieved, right? Because no matter how high we tune the proportional controller, that will lead to the shift of the magnitude plot vertically, it will not change the phase plot, where the phase plot of these double integrators, as you can see it here, it's always equal to negative 180 degrees all over frequency, right? That means no matter how high we tune the proportional controller, if we only use a proportional controller here, we will never achieve this requirement, because this phase plot, it's always equal to negative 180 degrees all over frequency. So definitely we need more than just a proportional controller. And because we want to improve the transient performance, I will choose to use a PD controller. Let me erase this first before we continue. So because we are not going to use simply a proportional controller, then let's restart again our thinking process now here. We want to have phase margin less than or equal 65.53 degrees here. Let's take a look now the second requirement. The second requirement says that the undamped natural frequency should be equal to square root of 2. According to one of the equations that correlates phase margin frequency to zeta and omega n, we can immediately see that the phase margin frequency requirement will be greater than or equal to 0.91 radian per second. Why is it like that? Because we want to have omega n exactly at square root of 2, but the zeta can be anything less than or equal 0.707. This means our omega pm, our phase margin frequency, can be anything greater than 0.91. You still remember one of the plot here that we also discussed a long time ago? The relationship between the ratio of phase margin frequency to omega n to the zeta, to the damping ratio there. The requirement of the zeta, the damping ratio, as what we have already discussed before, the requirement is less than 0.707. Let's say 0.707 is about this value, right? And this will lead to the requirement of the ratio between phase margin frequency and omega n about, this is about 0.64 or 0.6. I guess let's call it, this one is 0.64. This means because we have the first requirement, zeta can be anything less than 0.707. This can be translated then to the requirement of the ratio between phase margin frequency to undamped natural frequency greater than 0.64, right? So if we want to have zeta less than or equal 0.707, that means the ratio between omega pm and omega n can be anything between 0.64 to 1. The ratio between omega pm and omega n should be greater than 0.64. The ratio between omega pm and omega n, like what we have already discussed, should be greater than equal 0.64. That means my omega pm, because my second requirement says omega pn, my second requirement says that omega n should be equal to square root of 2, then my omega pm should be greater than or equal 0.64 times square root of 2. This is exactly equal to this one, 0.91 radian per second. Okay, so I have two translated requirements now. The first requirement is that my phase margin should be less than or equal 65.53 degrees. The second requirement is that my phase margin frequency should be greater than or equal 0.91 radian per second, right? But as an engineer, we don't really like a difficult number. So because the second requirement says that the phase margin frequency should be greater than 0.91, I don't really like complex number. What I mean by complex number, not a pretty number. So instead of setting phase margin frequency greater than equal 0.91, I will just simply, I want to set as a second requirement omega pm phase margin frequency equal to 1. 1 is greater than 0.91. So let's set this omega pm, the phase margin frequency equal to 1 radian per second, as our second requirement. Okay, so the second requirement is that omega pm phase margin frequency should be equal to 1 radian per second. Where or when this will happen? Phase margin frequency equal to 1 radian per second will be somewhere here. I indicated here in this Bode diagram. This dashed line indicates phase margin frequency equal to 1. This phase margin frequency equal to 1 radian per second will happen if, you still remember, this will happen if the magnitude value at this frequency is equal to 0 dB. By coincidence, this happened that the magnitude of my double integrator here is already close to 0 dB at 1 radian per second. Actually, if you zoom it in, this is not exactly equal to 0 dB, but by coincidence in this example, at this phase margin frequency, at the phase margin frequency equal to 1 radian per second, the magnitude is already close enough to 0 dB, but it's not 0 dB. In some other example, you might have a case where the magnitude is far from 0 dB. But by coincidence, in this example, the magnitude is already close to 0 dB at the desired phase margin frequency of 1 radian per second. But that is not the point here. The point is that at this phase margin frequency at 1 radian per second, apparently the phase margin is not 65.53 degrees, right? The requirement is that at that phase margin frequency, the phase margin should be 65.53 degrees or slightly less than that, right? But at the current moment, the phase margin is too far from 65.53 degrees. So what do we have to do? The phase value of our current system is always negative 180 degrees all over the frequency. What can we do with it? We have to change the shape of the phase plot in our Bode diagram now. So let's take a look again now a bit more detail. One of the requirements is we have already decided that the phase margin frequency should be equal to 1 radian per second. We have already decided, but in order to improve the tension performance, we have already decided that we are going to use PD controller, right? And the PD controller, the structure looks like this. The dynamic part looks like this. S plus ZC. We will introduce an additional 0 in our open loop transfer function. But as we have already discussed before, no matter how high we adjust the gain, if we are only using a proportional controller, we will never achieve the other requirement, the requirement of phase margin, which is where the requirement is that the phase margin should be not more than 65.53 degrees, right? But this will never happen if we are going to use a simply proportional controller. In order to achieve the second requirement, we need to introduce a controller here in such the phase plot in our new open loop transfer function will cross this point more or less. I don't know, this should be around 114 degrees, I guess. Should be around 114 degrees, minus 114 degrees. In such, our phase margin then will be equal to 65.53 degrees. So we have to introduce a controller that will bend the phase plot in such the new phase plot will cross minus 114 degrees. It's not 114 actually, it should be 114 point, let me calculate, it should be 114.47 to be precise, 114.47 degrees minus 114.47 degrees. It should cross this point. So we are going to introduce a PD controller. In such the new open loop transfer function, the phase plot will cross this point. And to do so, we have already decided that we are going to introduce a PD controller. The dynamic of the PD controller will look like this, right? So in order to bend the original phase plot to cross this point by introducing a PD controller, this means this height of the phase plot of my PD controller should be equal to 65.53 degrees, correct? In such, when I have already introduced this PD controller, after I combine these two phase plots, then the phase plot of my new open loop transfer function will be something like this, right? And then it will cross, I'm sorry, I might exaggerate it a bit, but in such, the main goal is to have the phase plot of my new open loop transfer function cross this point, right? So okay, so in this case then, the requirement of my PD controller is that the phase value of my PD controller should be equal to 65.53 degrees at the frequency of 1 radian per second, right? Radian per second. As we know that the PD controller structure looks like this, GC is equal to KC S plus ZC, and you know how to calculate the phase, the angle of GC will be equal to inverse tangent of omega over ZC, right? From these two requirements, from this requirement, it says that when the frequency is equal to the phase margin frequency, if the frequency is equal to 1 radian per second, the angle should be equal to 65.53 degrees. So from here, then 53. So from here, then I can define what the required ZC is. So that is the idea on how to design ZC in my PD controller. Once we have already defined ZC value, I can introduce the dynamics of the PD controller there. Let's take a look what the ZC should be. The angle of GC at the phase margin frequency at the frequency of 1 radian per second. This should be equal to 65.53 degrees. So from there I can calculate what is the desired ZC, what the required ZC. That means, so at this point I have already designed the dynamic part of the PD controller. We still have one more thing to decide, the KC value. But let's tidy up this plot first after I introduce the dynamics of the PD controller. Let me erase everything here. After I introduce the dynamic of the PD controller, then the both diagrams of the open loop transfer function will be roughly something like this, then, like the blue one, the one that I indicated as a blue curve there. So expectedly then, this height will be equal to 65.53 degrees, right? We have designed the ZC. We still have to design KC. I have already mentioned before, by coincidence at this phase margin frequency, the magnitude is already close to 0 dB, but in fact this is not really 0 dB, it's just close to 0 dB. So how to design the KC in our PD controller? You have to set the magnitude at the phase margin frequency, the magnitude of the open loop transfer function, to be exactly equal to 0 dB. So how we do that? It's exactly the same like when we are designing a proportional controller. You just have to find the magnitude of the current open loop transfer function, and apparently the magnitude of the current open loop transfer function, the double integrator in series with the dynamics of the PD controller is equal to 0.82 dB. That means we have to shift down the magnitude plot here by negative 0.82 dB. Negative 0.82 dB corresponds to 0.91 in linear scale. That means we need to introduce a proportional gain of 0.91. In order to what? In order to exactly make the magnitude plot crosses 0 dB line at the desired phase margin frequency of 1 radian per second. So we have already designed the dynamic part of the PD controller. We already designed the gain of the PD controller. That means we have already finished designing the PD controller in general. So our complete PD controller will be like this then, where the dynamic is equal to S plus 0.455 and the gain is equal to 0.91. That's how we design a PD controller. Just to conclude here, commonly, again, I have already discussed this at the beginning, PD controller is applied to improve the tension performance, to improve the dynamic condition. And the PD controller, the structure looks like this, right? Where the dynamic part of the PD controller is S plus ZC and KC is the gain of the PD controller. Design stepwise, we only have two steps. Basically, you have to design ZC to achieve the desired dynamic objective. For example, when you want to achieve the desired damping ratio zeta. And the second step, we just have to fine tune the gain of our PD controller based on the desired goal, and by adjusting the magnitude value at the desired phase margin frequency. So this slide basically concludes all of our discussion in controller design. I mentioned long time ago that there exists a combination of P, I, and D controllers together to form a PID controller. How do we design a PID controller? Basically, designing a PID controller is just simply a combination of PI design and PD design. PID, proportional integral derivative controller, is just simply a combination of PI and PD controllers. Okay, so this concludes all of our discussion from system theory until the controller design. In the lecture notes, anyhow, you can see that there are still a few more controller types. I also give an illustration of lead compensator and lag compensator. These two controllers is just supplementary to what we have already discussed up to this point. Okay, thank you for your attention and hopefully you enjoy the series of this video.